In order to be able to implement an optimal control strategy that tries to minimize the rate of SEI growth, would need a battery management system that can calculate the side reaction flux very quickly and accurately, because we've seen the side reaction flux is what drives the film resistance, and it's what drives the capacity loss also. Of course, we could do it by directly solving the coupled partial differential equations that are given by the Newman model coupled together with the Ramadas model. But that's going to be very complicated, very slow, not really robust enough for a real battery management system implementation. We need to make this JS model faster and simpler, and we really need a way to decouple it from the ideal cell model, this physics-based ideal cell model, because that's a coupled PDE system itself. So one possibility would be to glue this JS calculation onto the reduced order model that we developed last semester for a physics-based approach to modeling. That would work. But we're going to do something even simpler here. And that's one reason why I include this particular method in this course, where we don't focus too much on physics-based models, because we can implement the SEI growth model without the physics-based model, and that's pretty cool. So we're going to look at an incremental model. Incremental simply meaning that it's of the form that value at time k equals value at time k minus 1 plus stuff. It's a recursive model. It adds to itself. I don't have to remember infinite history. I just need to remember the previous value in order to calculate the present JS, present R film, and present capacity of a cell. The work that I present here is reported in a paper by Randall and Perkins, and the one that was listed in the previous section of notes in the footnote. And we used the same assumptions as Ramadas, and we added a couple more assumptions of our own in order to simplify the PDE model into a very simple ordinary difference equation kind of model. Assumption 1 is that the cell is assumed always to be in a quasi-equilibrium state, and that lets us compute the exchange current density I0. Remember, I0 is equal to its F times the reaction rate constant times CE, I think, to the 1 minus alpha, and then CS max minus CSE to the 1 minus alpha, and then CSE to the alpha power, if I remember correctly. Might be wrong. But something like that. In order to compute it in a dynamic situation, I need to know what is the surface concentration now and what is the electrolyte concentration right now at different places in the cell. But we're going to assume this quasi-equilibrium state, which says, well, the electrolyte concentration is always its equilibrium value, and CSE is the value defined at the present state of charge as the average concentration as opposed to the surface concentration. So we're neglecting some local variations in electrolyte and solid surface concentrations when we do this. The value that we compute for JS then really theoretically corresponds most directly to having a cell being at rest and then applying a sudden pulse of current of magnitude I applied, which is then constant over some time interval delta t, and we want to see how much degradation happens because of that. We will explore in the simulations in a later section, so we base our derivation on this assumption, but we'll see how well the simulations work when this assumption is violated, and it turns out that even in a dynamic setting, the model works pretty well. So this isn't a terribly bad assumption to make. Another thing that we assume is that the intercalation flux J and the side reaction flux JS are uniform over the negative electrode. So if this is the negative electrode, we're saying that J is flat. that it's not a function of x, not a function of space. And we know from simulations last semester that it's probably not completely true, because the intercalation reaction tends to do something like that, depending on whether I'm charging or discharging, where this is the separator, that's the current collector. So there tends to be more activity in the neighborhood of the separator. So we're approximating here by saying, nope, it's flat. And that allows us then to compute the J total, which is, remember, J total equals J plus Js, as the applied current to this cell divided by the volume multiplied by F times the specific surface area of the particles in that volume. We assume, and so that J total applies everywhere in the electrode. We're not making specific calculations at different places. We assume that the regular reaction anodic and cathodic charge transfer coefficients are equal. So alpha equals 0.5, and that's pretty commonly seen in the literature, so that's probably not a bad assumption either. And from these added assumptions on top of Ramadas's assumptions, we can make our incremental model of degradation. So this is how we're going to do it. We start out by determining the stoichiometry of the negative electrode on average. And so this is the lithiation state. So it's theta n min, and n is for negative, and this is what we would have called theta 0% previously, maybe, and theta n max is the theta 100%, maybe, for the negative, minus theta 0% for the electrode. So we're simply calculating the stoichiometry based on the cell state of charge of the negative electrode. Based on that, we put this value of theta n into the UOCP neg function of theta to give us what is our operating open circuit potential at this point in time. I say we're going to iterate to find Js. That's leaping ahead a little bit. So let's maybe not worry about that. But for now, you could assume maybe we initialize the value of Js to 0 and calculate an intercalation flux, and then somehow we would repeat this with a better guess of Js until I got a better value of intercalation flux. That's the idea of iteration that we could use to find Js. So we would say, okay, J total I know because there it is. And Js for the time being will initialize to 0, and we will set J, the reaction flux, the ideal reaction flux, equal to J total minus Js. By the way, this is just J total equals J plus Js rearranged, is all I've done here. So based on this value of J and the assumption 3, first, J is this Butler-Volmer equation. There's nothing too exciting there. Notice that alpha equals a half has been inserted here. That 1 over 2, the 1 over 2 is already in this equation. Because of that symmetry of the e to the 1/2 thing and e to the minus a half thing, this turns out to be equal to a hyperbolic sine function of this argument f over 2 rt times eta, except it's 2 times that, so I get this 2 out here because of this identity of exponentials. That allows us to solve for eta by inverting this hyperbolic sine. So eta is 2rt over f times the inverse hyperbolic sine of fj over 2I0. So now I've got an expression for the overpotential of the forward reaction, the normal reaction of this cell. This, by the way, is why we said that we had to assume that alpha was a half. If alpha is not a half, I can't go from that line to that line and have something that's easily invertible to give me eta in closed form. It may still be possible to do it using some kind of an inverse table lookup. I haven't really explored that, but alpha equals a half seems to work pretty well in practice. So I've got an expression for eta, and let's look at eta and eta s right side by side. Eta is the normal reaction over potential, eta s is the side reaction over potential, and there's an awful lot of similarities. They both have phi s, they both have minus phi e, they both have minus f r film j total in them. So eta s is really equal to eta plus this to get rid of that, and then minus this. And since I know what eta is, I said, oh, well, eta is this 2RT over f times inverse hyperbolic sine of fj over 2I naught, and then plus this reference minus that reference. We have an expression now for eta s. One important thing is that the film resistance, which is something I'm hoping to solve for, cancels out of this calculation, which really simplifies things a lot, and then I can add it back in later on. All right, we're almost there. I need to calculate the side reaction flux. So Js is side reaction flux. It's minus this IOS, the side reaction exchange current density, which, by the way, is usually a constant that we solve for by looking at experiments. So that's just a number, times e to the minus f over 2RT times eta s. Well, eta s I know, and I can put that in there. And expanding that out, I get this equation here. So Js is minus IOS over f times exp of minus f over 2RT times eta s. Well, eta s is this 2RT over f inverse hyperbolic sine of fj over 2I naught plus un ref minus us ref. Okay. Now in the next line, we said, hang on a minute, I know what J is. J, I have assumed, is equal to all of this. So I applied over AF times volume minus JS. So that's got plugged in. Great. Now in the next line, what we do is we recognize that e to the a plus b equals e to the a times e to the b. And we notice that I've got an exponential of this a term and this b term, if you will, that are themselves multiplied by this. So we're splitting out this part. And in the next line we have Js has that constant out front, and the exp minus f over 2RT times un minus us. The minuses switch things around, so I get expf times us minus un over 2RT. That gets factored out. And then what's left is the combination of all of this, and the f cancels, the 2RT cancels, and minus a sine h is the a sine h of minus something. A sine h is an odd function, so the negative comes inside, and I have the minus there, and this minus becomes a plus there. I get this whole equation. So we have, at this point, an equation that we can solve for Js. Now, it's not directly easy to solve for it, but let's look at it. IOS is a constant that's given to us. F is a constant. It's Faraday's constant. Faraday's constant, the side reaction reference potential, we're given that, like 0.4 Ramadas said. This reference potential we calculated based on the cell state of charge. That was our first step. 2RT is a constant. So all of this is a constant. That's why I factored it out. Then we have here I naught. We said we would calculate based on assuming an initial equilibrium. So that is a constant. AN vol n is a constant, and F is a constant. So I'm left with Js that I'm trying to compute being a function of itself, which is a little unfortunate, and the cell applied current. So for any cell applied current, it's possible to solve this equation to find Js. It's just a little tricky to solve for Js because it's an implicit nonlinear equation, but we can do it, and we can actually do it in a pretty efficient way, as we'll see in the next section. Okay, back up. Why did we go through this math? I want to know how much side reaction flux there is for a certain cell applied current, because ultimately I'm going to put this in an optimization that optimizes the cell applied current versus time to minimize Js. But for the time being, I just want a model that says for this cell current, this is how much side reaction there is going to be. So we can solve this, I claim. Once we've solved for Js, we can put this in our equations for film resistance and capacity loss. To do that, we assume that over our sampling interval of our model, delta t, that Js is basically constant, so we'll call it Js comma k for this kth time interval. We convert the continuous time model from Ramadas that said this is how the film grows into a discrete time version using the same kind of techniques that we looked at for converting continuous to discrete in the previous course. And we get that the new film thickness at time k is equal to the prior film thickness, and then minus the constant mp over rho times delta t, all times the input, which is this rate of side reaction. And we remember that Js is never positive, it's always negative or zero, meaning the film resistance is always, film thickness, is always growing. Film resistance, once I know film thickness, is easy. The equation that was given by Ramadas is this, and we can turn that into an incremental equation and find out that our film at time k is the same as our film at time k minus 1 minus this update factor by substituting this in for the change in film thickness over one time sample. And we can also discretize the capacity equation, which Ramadas had this integral equation, and we convert the integral equation into discrete time with our assumption that the capacity loss is uniform over the electrode. So I have a rectangular integral, so that new capacity is old capacity plus a constant times Js, and since Js itself is negative, that means the capacity is not increasing. So overall, the simplified model looks like this. Every time step, I first compute what is the stoichiometric operating point of the negative electrode on average. Then somehow I solve this equation for Js, and the only issue is that it's on both sides, and I need to be a little bit tricky when I'm solving for it. But I solve that equation for Js. And then I can update the film resistance, and I can update the capacity of this cell. And that's it. So this is a very simple, very simple model that there's no differential equations, there's no PDEs, anything like that. It's purely algebraic once we figure out how to solve this, which we don't yet know how to do, but that's what we look at next.